All right, so let's talk about part 3, image restoration. Okay, so here is the deal. We have done part 1, college physics. Part 2, simulation, show you some tools. Part 3, okay, that's the big deal. How do we recover image? So to start the story, last summer, my students, Xingguang and Zhuyuan, they brought my camera and to Provincetown, Indiana, and they had a fun summer. Down in a hot day, taking many pictures, and suffered from sunburn. Zhuyuan, do you get sunburn? A lot of hard work. And I can tell you how difficult is this experiment. You feel, okay, so if you've never taken a picture for long distance, I can tell you why it's so hard. You set up your tripod, you put up a camera, you set up your lens. Okay, the moment you start to zoom into the object, the wind blows your camera. You feel like, oh, how come the wind is enough to blow the camera? Cannot be, right? The camera is so heavy. Now, don't forget that you're looking at someone that is about 1,000 meters, 500 meters away. And you are zooming in so much to that person. Okay, and so the field of view that you have is very narrow, just to that person's face. Okay, in this case, it would be the text, very small text. So the wind doesn't need to be too strong, just blow a little bit. Boom. Okay, your head camera shakes a little bit, you're completely off the screen. Okay, that's one. Number 2 is that for this kind of lens, we are not a very wealthy lab, so we can only buy a lens with a couple $100. So what it means is that you don't have any auto focusing function. So now you're zooming into an object and then you start to tune your lens. It's very difficult to get focus because you move the lens by a little bit amount, you're out of focus. You take it back a little bit, it's out of focus again. So to get to the point of focusing is very hard. Okay, so that's the image capturing part, and also not talking about the ground truth and also the number of scenes and so on and so forth. So there are lots of difficulties to capturing data. All right, so let's come back to our problem. Here is a real image that we captured in one summer. Usually you capture a video, and then here is the recovered image. Okay, so we want to go from here to here. Now you may observe a couple things as you are doing this problem. Blur is the one thing, right? I mentioned that's a blur. The other thing will be the pixel displacement, what I call it the tilt, right? Tilt and blur. You have these 2 effects. So if you want to recover the image from this video sequence, what you need to do is to overcome these 2 issues. So for anyone who has done image deconvolution, I believe this equation will look familiar. You have an underlying image X, and then you have a point spread function H convolution and some additive Gaussian noise. You want to recover it. You solve this alternating minimization problem, assuming that you don't know the point spread function. This problem can be solved, and I would say that most of our efforts for the past 20 to 30 years has been spent on regularization functions, in particular sparsity related stuff. Okay, we spent a great deal of time over the past 2 decades talking about optimization algorithms. Right now, it will be data and training. The core business for Turbulence has nothing to do with these. It has everything to do with the forward model. The forward model is so hard that you cannot easily invert it. So what do I mean by forward model? The forward model, of course, doesn't follow this equation, right? We know what is the forward model. I give you an image, you need to go through the split step, or you go to our simulator, it will be that kind of forward model. So what does it mean? Well, if you go with split step, you need to go from Fresnel to Kolmogorov, Fresnel, Kolmogorov, all the phase screens. I can abstract it, write it as y equals to a operator h, okay? Apply that to an image x. No matter which model you use, no matter which simulator you use, you have this forward model. And this h is nonlinear, stochastic. Every moment it changes. How do you do that? So let's think about this problem, right? So let's forget about the randomness for a while. Okay, just think about the blur and the tilt, pixel displacement and the blur. Just these two issues. We can go to the Zernike space and we look at the Zernike representation. We can sort of decouple them into blur and tilt, right? Now, then you have a question. The forward model should be blur first and then tilt, okay? B first and then T, or tilt first and then blur, okay? All right, so let's do a poll here. So that's the beauty of having in person. How many of you will vote for B, T, tilt first and then blur? Okay, hands up. B followed by T, B and then T, okay, yes. So that's the equation, tilt first and then blur. Okay, so I see one hand. How about the second one? T and B, the second equation. Okay, so more. Okay, so blur first and then tilt. Great. Now, some of you haven't raised your hand, which is fine because it is extremely confusing. Okay, it is extremely confusing. Even I was extremely confusing. I can tell you that a couple days ago, he and I are still debating which one is correct. Nick and I are still debating which one is correct. And so I think today we have a conclusion. I can tell you which one is correct. If you go to the literature, you can see there are work using B and T. There are work using T and B, more on T and B. These are mostly applied math and also more towards computer vision. So these are the papers. This is published in PAMI, more signal processing, and they do this B, T. Usually there is T and B. For the OSA people, surprisingly, they never talk about this B and T and B. they just use H. That's the Optical Society America's difference compared to us, which is interesting. Of course, this is the most accurate one. But the reason that we want to talk about B and T and B is that we want to decouple the two. We want to separate the two, and because we know handling the blur, handling the tilts, if you can do this separately, it's a lot easier than do them together. So that's our motivation. All right, so let's look at the business. If you blur first and then tilt for this image, with this blur kernel, now I'm assuming a very simple blur kernel. That's a invariant blur kernel. Every pixel they're suffering from the same blur. Okay, you have the tilt map. The tilt map is per pixel. You take this input image with this blur kernel and this tilt map. You blur first, then tilt. You get this. You tilt first, then blur. You get that. Very different. You ask which one is correct. This one is correct. The bottom one is correct. Let me explain why. Okay, so you need to follow me. Do some mental calculation. Okay, so the input is a grid of points. Okay, a grid of points. Now you want to apply a blur to this grid of points, and then this blur will be shifted. Right, the blur will be shifted because of turbulence. So you have a point here. The blur should be blurring that point, and then you need to move that pixel to another location, right? So the blur has to move. Remember, the blur has to move. Okay, you look at the yellow example here. You first move the location of the pixels, and then you apply the blur to each individual. Then you're moving the blur to a location. How about this case? You blur it first. And remember that the tilt map is not defined just on those grid points. The tilt map is applied to every single pixel of your image. So you apply the tilt to this blur, then you're making the blur become something else, right? So B then T versus T then B, they're different. Okay. So now I'm offending a lot of people. I know I'm offending a lot of people. This is correct. This is unfortunately not correct. Okay. According to the analysis here. But I want to make another remark here that you can still do that. Okay, you can still do T and B. You can still do that. There's a reason behind it. Although if I would say why shouldn't we do it anymore? I will comment on that. Okay, so here is more illustration. Okay, so you have this set of points. If you move the points first, and then you are just recalculating the blur at the new grid of points, right? So you still get the blur. Here you're really destroying the blur. If you like equations, and here are some equations. You do y equals to hx. That should be the correct blur equation. Okay, so that would involve all the shift and also the blur. So that would be the right one. So now if you apply T and B versus B and T, I'm not going to go through all these numbers, right? But you can just sit down for 2 seconds to realize that this one is the same as that one. This one is not. Okay, that is also explained by the picture before. So these two are equivalent. This is not. Sorry. Okay, so does it matter? Yeah, it does matter if you care about the accuracy. It does matter if you want to do simulation. It does matter if you're not presenting in CVPR, but you're presenting OSA. It does matter, okay? Because they're different, and one is correct, the other one is not correct. In practice, okay. So the question here is, can we just use the true model for simulation, right? Why do we want to use any one of these? The reason is that it's not about speed. It's all about the computational complexity. Okay. If you don't do that, even for simulation, it's gonna take forever. All right. So here is another experiment. We have 2 pairs of images. Okay. Each pair will have T and B and B and T. Okay, just honestly tell me that if you can see a difference. Okay, anyone can see the difference between these two? Okay, anyone cannot see a difference between these two? Okay, I vote 2 hands. Okay, okay. So here's a very simple experiment. Just show this image to your parents. If they can tell there is a difference, there is a difference. If they cannot tell there's a difference, that's really not difference. Okay, so here is the calculation. You have Cn squared equals to 10 to the power minus 15. That's not too bad, but it's not too good turbulence. Okay, there isn't any difference between these two. Now you say, why? Why? Well, previously you showed me that the blurs, they're all destroyed. How come when you apply the technique to this image, you don't see it? Well, because in the previous case, it's a very, very special case. You have a point source that everything is so amplified that you can see the effect. Here, when you have a real image, you have edges, you have content. When you have the destroyed blur, you have another destroyed blur sitting right next to it. And so they add up together, and so the effect is less obvious. Now, of course, you can zoom in really, really hard, and then you can see some difference, right? You can see some difference, but there was a really, really tiny bit of difference. And so what it means is that, yep, one model is the correct model. The other one is not the correct model, but fine. As far as realization is concerned, they are very similar. So how about solving inverse problems? Will one give you a better solution? Let's think about that, right? So if I go with B and T, so it means that when I solve the inverse problem, we need to take care of the blur first, right? Because when you take the inverse, it will be B inverse applied to Y, and then you take T inverse, right? So that would be the inverse problem. If you have ever done deconvolution, you would say, easy problem, because B inverse, that's deconvolution, download a deconvolution network, and then I just need to take care of the tilt. That's not the case because 5 minutes later you cry because the B is spatially varying. You have a lot of these B's, and so removing the B's is very hard. And then removing the T's is also hard, right? How about T and B? Well, that's not the right model. But if you ever want to solve an inverse problem, removing the T is actually easier. Okay, why? Because optical flow and the tools that we all like about, right? Those can sort of handle the displacement of the pixels, right? So removing the T is actually easier than removing the B first. And if you can remove the T, the B, I can show you that the blur will be slightly more stable. You get some kind of invariant blur in the end. Okay, so I'm putting this face here. It's not that correct, but in terms of solving inverse problem, it's actually quite convenient. So what should we do? Here's my recommendation after so much debate. We should all acknowledge that the true model is the true model. Okay. This is the right model. This is the equivalent model. If you ever want to write an equation, right, in your paper, in your next CVPR paper, you say, okay, this is turbulence. Don't say that the turbulence comes from this equation. Okay, you should always say that the turbulence comes from this equation. Okay, because these two gentlemen tell you, and they have a proof here to show you that this is the case. And then you can say that as you're solving inverse problem, that one is very hard. And so I'm taking the other approach. I'm using this one as I'm solving inverse problem. I fully acknowledge the discrepancy, but I'm using it. And if I can give you good recovery, it's a good recovery. It's a good solution. So that's the difference. When you write a paper, say that this is the true one. This is not correct, but then some inverse problem is a good approach to take, right? And they are all valid. Again, more comments again. A lot of debates again. Advantage of not using GAN, of course, I will advocate the physics-inspired perspective, and also it's faster, no black box, transparent, these things. The other thing I would want to comment is why GAN, right? People always say, why not GAN? I would say, why GAN? Well, you should give me a reason why we want to use GAN. Not because I'm more physics-based, but because we should ask, what is the advantage that the GAN would offer? Well, GAN will offer you approximation. Right? GAN is really powerful in approximating things, things that you are not able to observe that can approximate. GAN is also very good in being differentiable. Right? You want to put it into a network that's differentiable, is of course useful. Are these two things not doable using my physics-based simulator? We can ask, right? Approximate, we don't need to approximate because we're fast enough. Right? Unless you can show me that the GAN is even faster than ours, which I think it would be a good study to see how fast the GAN would become, right? But then we're already doing a lot of approximations so that it is fast. So right now, I don't see, there will be some rooms for improvement, right? But then the GAN has to show me. Another thing is differentiable. The current simulator is differentiable. When we implement it in PyTorch, is differentiable. Okay, so it's already there. So then it becomes less, I have less incentive to switch to GAN. Plus, there's always a question of how valid is your GAN, about tracking the statistics, making sure that the two statistics, they match the theory. Just imagine that you're not presenting in this room, you go to OSA and present, what would be the comments from your audience, right? So think in that way, then that would be the evaluation and also the verification that you need to provide. Okay, so how do we do an image restoration? Right now, we know which model is correct. We know we want to separate them, remove the tilt first, and then we do the blur. So I'm going to comment on these two things, right? One is removing the tilt, the other one is removing the blur. So two principles, lucky imaging and the blur. Let's talk about lucky imaging. This is a technique that has been here forever, since the beginning of astronomical imaging. Why? Because when you take a picture of a star, the turbulence will shake your image. and from time to time, you have a lucky moment. Okay, okay, the Jupiter looks sharp. Okay, so that's called the lucky imaging. If you look at the point breadth functions over a large field of view, you will from time to time you will see one point it's just a delta function. Delta function means that there's no blur. Okay, from time to time you will see that. If you can pick that up, that would be your lucky image. Those lucky images, they would be sharp, no distortion, no displacement, very good. So how do you get the lucky effect? Well, why do you get the lucky effect? The reason is because the random process underlying the turbulence is a zero mean Gaussian process. Now, the zero mean Gaussian process is given by Tatarsky and also Kolmogorov. Okay, the zero mean approximation. So you know it's zero mean. Therefore, over a long period of time, the ensemble average, we take a long period of time, that it will become zero. So the distortion will be centered at zero. So from time to time, you will hit that point. Now, do you observe a lucky effect? Yeah, you do observe lucky effect. So let's say in this example, you put a burner. Okay, you take a camera. You will see lucky effect, and in fact, the lucky effect will be over the entire image. Okay, entire image will be sharp. Entire image will be blurred. If you're taking the camera out for 500 meters to 1,000 meters, you will not observe that. Now, there is a reason. Why can I observe lucky image when I put a burner? Why cannot I observe the lucky image as I'm seeing long distance? When you're looking at long distance, you will not get the entire image. You will get the lucky region. Okay, only a very small region of the video will be sharp at that instantaneous moment. Okay, so that is the effect. So why? Well, because in turbulence, there is a concept called the isoplanetism versus anisoplanetism, which I will briefly explain that. When you are talking about long range, well, all the pixels, they are shifting around. Now you're asking everyone to be synchronized to give you delta function. Everyone has to give you the same delta function, but that probability is extremely low. Right? So back in the 70s, David Fried did a study. He was looking at one point. Okay, he called it the lucky frame, but that is really inside a small region. So it is all. It's what we call the isoplanetic angle. It's within that angle. And so it is only one point. He has a formula. He said that the probability of getting that lucky image is given by this formula. And you can trace this line. If you're talking about 10 to the d over r naught is usually about 1 to 5, then there is a reasonable chance of getting a lucky effect. But if your turbulence getting stronger and stronger, no, you don't get a chance at all. Okay, and now over this range, now you can see that this is a very, very narrow range that you can do things. Very narrow, right? We're talking about d over r naught is between 1 and 5. This scale is going to 200. So who will go up to 200? Well, if you do optical communication, satellite to Earth, Earth to satellite, that kind of optical communication, you need to go through this kind of turbulence, and those are really coherent source. They have laser, big power laser. For us, we're taking cameras outdoor, taking pictures. You cannot do anything beyond 5. Okay, beyond 5, d over r naught beyond 5 is not doable. Okay, so two concepts here: isoplanetic turbulence and anisoplanetic turbulence. Isoplanetic turbulence is a very, very tiny field of view. Very, very small field of view, is that all the pixel displacements they share. Okay, and also planetic turbulence, it would be the thing that we care about. Every pixels they distort it differently. How can we do lucky imaging? Of course, we're gonna do it on computer, but if you care about hardware, then in physics, in astronomy, they actually build hardware devices to do this lucky imaging. The concept is very easy. You look at the star, you look at Jupiter. okay, or you look at in Mars, you look at something that has turbulent effects. Look for a nearby star that is brighter, that doesn't have the turbulent effects, right? Treat that as your point source, and then measure the phase delay of that point source, and then have a deformable mirror to compensate for the phase delay of the target, right? So they usually have a reference, have a target, use the reference to calculate, and then shoot for the target, right? So you can compensate. Now, this compensation means that I look for delta functions, right? So that is the lucky imaging techniques on hardware. Digitally, you can do sort of similar things by optical flow, okay? So you start with an image, then you sort of assume that the pixel has moved, then you grab a patch, you move around the image, or usually it's a video, you move around the video to look for the same patch in the video, and then you have some kind of metric. Usually it will be how sharp is that patch. Now, of course, you cannot do this for the sky or flat region, that you cannot do. But for building, where you have an edge, for corners, then you can say, okay, it should be sharp. So how sharp is that patch? If it's sharp, I will keep it. If it's not sharp, throw it away, right? So this is the digital lucky imaging. And at the same time, you will also align the patch, right? Because imagine that the pixels, they're shifting along the path in time. Then you can, as you are grabbing similar patches, you align them, right? So the alignment is done by optical flow. So this paper is published back in early 2010. So what they do is that they do this non-rigid image registration, which is what I'm describing, and then they pick up the sharp patches. They form, they construct this, what they call the diffraction limit of blur. So their argument is that after I have taken all the sharp patches, then the image that I have constructed will only have some residual blur. Those blur will be spatially invariant. Then you can apply whatever deconvolution technique you want. You can do that. Okay, so that's one technique. A similar technique that is also pretty good is called the Fourier burst accumulation. In this paper, what they say is that I have a sequence of videos, okay, video frames, and each of them, they are distorted by a different point spread function. And I can go to the Fourier domain, okay, of the image. And then what I can do is to form this weighted average. Now, why? Because if you are blurred by a delta function, then the spectrum has to be bigger, right? Because that's just the image. The image will have some kind of spectrum, right? So if the image is distorted by the delta function, the image is still there, and so the spectrum will still be pretty wide. If you are distorted by a pretty bad blur, then it will be low pass, and so lots of high frequencies will be gone, and so your spectrum will become narrower. And so as you're constructing this weighted average, you just keep the strong parts. As you see more strong components, keep them. Weak components, throw them away. So you start to form this average. Then the resulting results, right? So the ultimate spectrum will have all these strong components added together. So that will be closer to this delta function effect. This is what they claim. And it's going to give you some reasonable results in terms of recovery. Complex wavelet, that is another very powerful technique. So instead of using the Fourier transform to do that operation, you can do a thing called the wavelet transform. And there's another thing called the complex wavelet transform. So you can look into the literature and see what they do. Another thing that this paper mentioned is to do a region of interest. So they were saying that usually you have a moving object, so just look at the moving objects, and then you do the work over there. You can do a BM3D type of operation, block matching, that kind of operation. Essentially, you do the search using a block, okay? And then you group the blocks together, and do the thing. all these techniques, most of them, they apply to static scenes. If you apply the same thing to moving scenes, you will suffer from smoothing out the moving object. The reason is this. This is the space-time trace of this horizontal line. Clearly, you can see there's a jittering, vertically jittering. So this is the time axis. So as you jitter, that means turbulence affecting your pixel value. This is the man, right? So I have this horizontal line here. So this is horizontal cross section. The man is moving, but then the jitter is here. You need to separate between the moving object and also the turbulence, and that is usually the hard part. Okay, oftentimes you will remove the person. So some paper has done some work. What they say is crop out the moving person, don't touch him or her, recover the background. Now, the sad reality is that you don't care about the background. Okay, you care about the person. So you take out the person, you don't do anything about the person, you recover the background, and then when your funding agency comes to you, what are you doing with the person? You say, I've not done anything. So that's the sad reality. We do have some preliminary results. I don't think it's too good, but it's still okay. You sort of want to do the space-time non-local search, and also you want to construct the average. Okay, so it's sort of similar to what I'm describing before. As you are looking for sharp patches, you also look for relevant patches, and so you set up a space-time window to have some kind of window size. You see, there is something. If there is a thing that looks similar to you, you will keep them. You construct a reference, and then you do the optical flow against the reference. Okay, so I can tell more about this maybe offline. How do we exactly do that? But for the time being, I also want to talk about the blur. Okay, so the previous part, it will be a lot of techniques that deal with the tilt, right? You do Fourier burst, you can do the alignment and so on. How do you model the blur? Well, of course, deep neural network, but then we also have some physics inside this problem. For example, we know that over a long period of time, the point spread functions will become the average, and that's called the long exposure point spread function. There's an equation. Okay, there's an equation for this point spread function. This is the optical transfer function. Okay, in the Fourier domain, there's an equation, and we can use that. There's also a short exposure equation. See, so we have equations for these blur. Can we use them? The answer is not quite, because after you have removed the tilt, you still have residual blur, and the residual blur is not given by this equation. So you cannot exactly use this thing. What we can do here is to do some kind of offline learning. Okay, so this is a technique that we find pretty robust. You're still solving this alternating minimization, right, in the traditional deconvolution setting. But you have some prior knowledge about your blur. So this is your H is your blur. The blur, as I said, the blur is coming from some kind of basis functions, right? So you can you can say that, okay, the blur is written as a sum of basis functions. So these are the bases. I can learn it from some PCA or some Gaussian blur. There will be coefficients, right? Wj in this equation here. And I can sort of do it offline. I can find out the statistics of the W's. These are the coefficients. And I can show you that the W's, they are distributed not according to Gaussian. The W's, they draw according to some kind of a Laplacian. That's a L1 norm for the W. And there is also a hyperparameter sigma. So it's a weighted L1 norm of the W's. So once I know the W's, UJs, they are predefined, then I can construct the H. So you do have a prior for the blur instead of using a completely blind guess of the blur. So with this kind of model, you can get a little bit better, not significantly better. You can get a little better. Of course, whenever you write a paper, you will say, well, I do better than the rest. I have a higher number. So that's the usual practice. I would say we do slightly better, just slightly better, not significantly. Okay. So it says that the prior does matter a little bit. Okay. In terms of image reconstruction for synthetic case, you do see a bit more. For real case, you can recover narrow objects a bit better. So that's what we are observing here. So how important is the deconvolution step? I think it is very important. But it requires a good lucky fusion step in the beginning, because if you don't do the fusion step right, then the blur will be too bizarre to recover. Limitations of classical methods, the blur is still spatially varying. It's just spatially varying a bit. Okay, so you still need to use deep learning techniques to overcome those bottlenecks. Lucky steps has a lot of issues. You can see how difficult that problem is. A lot of problems with camera captures, image capture. Removing the blur is not enough. You need to also do some super resolution. That's what we are experiencing right now. Okay. The hard part is moving object plus small object plus strong turbulence plus poor optics. That is very difficult. Okay, so I have 5 more minutes. Okay, so I will talk about deep learning. Okay, so that is also pretty relevant today. Okay, so the omnipotent deep neural network. That means you can solve every problem, right? So deep neural network, of course, can solve turbulence. A lot of work. Some observations I have so far with deep neural networks. I'm not going to talk about the specific architecture because it's changing every day. And there are more coming. We are also publishing, and other people are publishing. So you just cannot keep track of the network architectures. Okay, let me put it this way. But there are some observations I have seen so far. The neural networks appears to have quite a bit of generalization problem compared to classical methods. Classical methods, they are not trained on a particular data set, and so they don't perform well everywhere, but they don't fail everywhere. For networks, if you train on phase, it starts to perform pretty bad on license plate. So that's a generalization issue. There are other problems besides this class issue. You have different optics. I use this camera, uses that camera, this lens, that lens. I'm shooting images on this day versus that day, how much distance, and so on, right? So that will also affect your generalization. Unseen, wide range of conditions. Those are problems. Any solution? I don't have a solution. Okay. If I write a CVPR paper, I would say I have a solution, but I can tell you I don't have a solution here. Very hard problem. Generalizing to a wide range of turbulent conditions and then different classes of images. Very hard. We don't have a solution. What we have seen so far that seems to work, okay, is that the simulator plays an extremely big role here. If you have a good simulator, you can synthesize a lot of images. You can cover a wide range of conditions. If your simulator doesn't work, then the number of cases that you can cover will be a lot more limited. You need to do a lot of data augmentation, a lot of data. You need to adhere to physics. You need to use as much physics as possible so that you can be more robust to various conditions. You better train with generic content if you are not certain which scene that you're going to apply to. But if you're looking at phase, of course, train with phase would be a lot better. From our experience so far, GAN, if you just use GAN as is, it will have a bit worse generalization. But I think GAN is improving every day. So we might be able to use GAN in some of the modules. That could be a hope. Okay. A lot of people have suggested us to try transfer learning, zero-shot learning, these techniques, just because you don't have the ground truth. You only stuck with the distorted image. So some of these newer techniques could be used, which we don't have any experience, but I think it would be good things to explore. Importance of simulator, I have mentioned this before to you, and here's another example that we use one simulator versus the other simulator. This is our simulator. You can see that the recovery is actually quite different in terms of the image quality. Differentiable or not, you do want to have some differentiable simulator. In our case, I think it is differentiable, okay? And we have actually just shown that it is differentiable. Julian told me a couple days ago it is now differentiable. If you have a differentiable model, you can put into any of these algorithm unrolling techniques that you can solve the inverse problem. We're still working on that. Some of the latest results from our group on some undisclosed method, because right now there are bans on whatever venue, okay? I don't want to comment which particular venue we submit to. There are multiple venues. They have this kind of social ban, so I'm not going to tell you where we're submitting to. But we do have some results. This is a recovery, okay? So real image, and then this is the recovered image. These are the real video sequences, recovery 1, 2, and 3. Okay, so we're able to see something. Here is a comparison with a classical method clear that's based on complex wavelet. I think if you zoom in a little bit, you can see more of the noise that are residing in this clear results. We do a bit more better job in terms of removing the noise. Lastly, I want to comment on evaluating your algorithm, because I know some of you are developing your own turbulence mitigation method. Data is scarce, it's difficult to get, okay? So we are helping the community to put up some testing data sets, so you can have some real data to play with, open source, okay? Measuring the turbulence strength is hard because we are not rich. We cannot buy the scintillometer to measure the turbulence. It's also pretty nightmare to operate this. I hear from our collaborators. So we don't have a way to do that, but we can capture a lot of images. Also, we have built this. That could be useful to the community. It's a heat chamber that we put in Purdue. So we have 3 heat light boxes that our students they build by themselves, and then we have a monitor here that is displaying the point sources. Then we put a camera and we take a picture. Here you can display whatever image you want, right? You can show up an image, net image. Then we can take a picture. We will show you the distorted image. This one I want to comment a bit. What kind of image would be good for evaluation? If you want to get PSNR, if you use our simulator, then image like these would be okay. But in many cases, if you want to be more realistic, then the PSNR is pretty bad. I can tell you from my experience, pretty bad. You talk to any people doing turbulence restoration in DOD and DOE, they cared about resolution. They cared about resolution. So the standard thing they ask us to do would be how much can you recover? Right? By how much I can recover is that you really put up this resolution chart and see which level that you can recover. Now, a remark here is that, guys, please don't use GAN in this case, because if you use GAN, you train on this image, of course you can recover, but let's don't cheat. Let's don't cheat and see how much we can recover. So this is another evaluation scheme that we can use. Is the text. There's some good things about the text. Is because you can control the font size, font type, contrast. You have full control over that. There's also resolution, well-defined resolution. You don't have any crazy texture like the hair of this baboon. Not much color, then you're really testing how much your algorithm can do. Again, the comment here, don't cheat, just use generic data to train your model and see how much you can do. If you use text to train and then recover the text, of course, you can do much better than generic model. But that's not the purpose here. We want to see how much your model can perform. You can also use more downstream applications for a metric. For example, biometric, that could be one application you can do. Detecting the face, identifying people. Those would be a bit more application specific. So the evaluation metric will also be application specific. So usually my experience working in this field is that you need to have multiple evaluation scores. So as you are writing your paper, tell people more. Okay, for this experiment, this is the number. For that experiment, is that number. Okay. As a reviewer, as an editor, I usually just try to see, okay, how well you perform. And in many cases, I would say you don't have to beat state of the arts. As long as your method brings some insights, I will be very happy to see the paper accepted as an editor. Now whether other reviewers, other editors, they may have different preference, I cannot control, but that's at least my view on this topic. It's a very hard problem, so I think we should encourage more paper to be published. Okay, so looking forward, some concluding remarks for this tutorial. There are a lot of open problems. These are some subjective selection of problems that we are facing right now. Some of them are problems that we're working right now. We're working on methods to do variance in square profile. So you're looking at a long range, the profile changes. You're looking up the sky, satellite imaging, the CN square profile changes. How can we do that? So we're working on that problem. Depth dependent model, that is also very relevant because if you're not that far away, you're looking at car on the road, the depth actually matters. Okay, as the car is coming to you, the turbulence changes. If you have two cars, they should have two different profiles. So that will require you to have access to a depth map. So how can we do that? That's open question. I show you a simulator for 512 by 512, 10 frames per second real time. We're working on much bigger resolution, and I think that's doable. Much higher resolution, full HD image, real time simulation without interpolation. I think that would be extremely useful for the community. We are building differentiable models. I said the differentiable model is here, but then putting into the reconstruction, that is a challenge. Mitigation algorithm, if you are interested in working on this problem, the hard problem is now small objects, moving objects, and strong turbulence. That is the difficult problem. Generalization to unseen conditions, that's the issue. We, Purdue team, is really advocating for physics-inspired algorithm, but we're open to deep learning approaches, especially those physics-inspired deep learning approaches. I think that has a lot of hope. We believe that accurate data augmentation is essential. Okay, from my experience, that when you have a appropriate simulator, you can get a lot more from the reconstruction point of view. We encourage you to think about single frame versus multi-frame. For multi-frame, you can do lucky imaging. Single frame, you're stuck with that particular random realization. So you are limited. So depending on the applications that you are facing, you should think about whether you should take videos or you should take a single image. If you can take the picture by yourself, think about what kind of optics you want to use. Think about what kind of exposure you want to use. We think that restoration needs to be integrated with downstream tasks. Just because you don't want to just train a restoration network for the sake of restoration network, you still want to solve downstream tasks. So maybe some kind of multitasking training would be helpful, right? So you're not just recovering that image, you also want to make sure that the recovered image will have some positive impact to your downstream task. So multitasking training would be something to explore. So that concludes this tutorial. And if you look at the slides, I actually spent some time to put up all the references, not all, but quite a bit of references that we use. That includes monographs. Follow us closely because we will have another monograph that will be about 100 to 150 page that will be submitted somewhere, and I will put it on archive, and so the community too can look at this. That will be based on the set of slides. And then there are classical physics papers, a whole series of papers by David Fried, a lot of papers on turbulence data sets, simulators, okay, different types of simulators, reconstruction algorithms. That is more because I know this community, we cared about more about the reconstruction methods. So there are a ton of these methods from classical to deep neural networks. You can see the list keeps going. Okay, so I hope this list will be useful to you. And finally, we have our publications. If you go to our website, you can see that. Pending papers 1, 2, 3, 4. Okay, so we have those lining up. With that, I want to thank everyone for coming to this tutorial. We will post our tutorial online. After I come back, go back to school, I will edit the video a little bit, and then I'll put it online on YouTube, and everyone can watch. So help us spread the word to your friends and tell them that this tutorial will be up online. If you're working on problems similar to this type, let us know. We'll be very happy to chat. We look forward to have collaborations with many of you here. Okay, thank you very much.